Alright, so this chapter is on work and power. So we're going to start out with the idea of work. Okay, so what is work? Now, to a typical person, the idea of work might mean something that you go and do to earn money. So you have a job, you do work, and you get paid for it. But the physics definition is different. The physics definition is the force applied through a distance. And so hopefully you remember that we talked about in the previous chapter that force is a push or a pull. So work is a push or a pull applied through a distance. So if you push it against a desk and nothing moves, then technically you have not done any work. So we're going to talk about the circumstances in which work really happens. So when are you technically, according to physics, doing work, and when are you not doing work? Because according to the definition, work is force applied through a distance. But there are three conditions that actually have to be met in order for you to truly say, hey, I'm doing work according to physics. The first one is that you must be touching the object. Or not necessarily, I guess, you don't have to use the word you, but the objects must be touching. So if there's no touching, no work. The other two, the applied force must make the object move. So if there's no movement, no work. Okay, so it has to move in order for work to be done. And then last but not least, the work and the movement have to be in the same direction. So, and we'll talk about this in class a little bit, and I'll show you a demonstration. But I have an example here. So if you lift a stack of books upward, okay, then your books move upward, and notice that that is in the same direction. So that means work has been done. But if, let's say that you lift the books up, but you're moving the books this way, there's no work because look, one of the arrows is this way, one of the arrows is this way, and so they're different directions. And again, I'll do a real life scenario in class to make a little bit more sense of this, but for now just know that the movement and the force have to be in the same direction. Okay, so like everything in physics, there's an equation. So W equals FD. So the work, which is in the units of joules, that's a new unit for us, abbreviated by capital J, is equal to the force. The key here is force, which force is in newtons. We've already talked about force in previous chapters. And then times distance, which we've talked about distance as well, which is in meters. So W equals F times D. So let's talk about some example problems here. Alright, W equals FD, W, F, D, which we've already went through what each of those letters mean. 75 newtons, let's see, read the problem. A force of 75 newtons is exerted on a 45 kilogram couch, and the couch is moved 5 meters. How much work is done in moving the couch? 75 newtons is the first thing they gave us. Newtons is a force. Then they gave us this 45 kilogram couch. And just to review, work is in joules, force is in newtons, distance is in meters. Is there anything in kilograms? No. Extra gobbledygook that we don't need. Last but not least, they give us this 5 meters. Distance is in meters, meaning that they give us everything but the W. So in this case, W is equal to 75 times 5, or W is equal to, take our calculator, 75 times 5, 375. And for W, the label is joules. Here's another example. Same equation that you're using. So W equals F times D. So they give us a lawnmower is pushed with a force of 80 newtons if 12,000 joules of work are done when mowing a lawn. What is the total distance the lawnmower was pushed? So they give us 80 newtons. Newtons is a force. In this case, though, they give us 12,000 joules, so 12,000 joules is the work being done, so we want it to find the distance. Okay, so in this case, 12,000 is equal to 80 times d. So look at that, you have everything but the d. That means you're going to divide. So take 12,000 divided by 80. D is equal to 150. Distance is in meters. And there you go. Last but not least, one more example. If I hit pin, W equals F times D. Okay, the brakes on a car do 240,000 joules of work in stopping the car. If the car travels a distance of 50 meters while the brakes are being applied, what is the total force of the brakes exerted on the car? 240,000 joules. So 240,000 joules. They give you 50 meters, which is the distance. So that means you're going to divide each side by 50. F is going to be equal to, in this case, 240,000 divided by 50, or 4,800, and it's force, so it'd be in newtons. So there's work. Alright, power is just the rate at which energy or work is converted. So, we have a power bill that tells us how much we have to pay for the amount of energy we use over a period of time. That's exactly what we're talking about here. We measure energy in the terms of watts. So the number of joules that we use per second. And of course your power bills are not per second, because if so that'd get a little crazy. And a lot of times even in your electric bills we use higher units because, we use a lot more power than what we talk about in these simple examples. But power is in watts. We have energy in joules. Now sometimes we even, instead of using energy, and I even replace that in the definition, we use work, because work is a type of energy. And it's a specific type of energy. And then you have time on the bottom, which we put in seconds. I refer to this a lot as the PET equation, because look, P-E-T. Power equals energy over time. P equals E over T. PET equation. And of course, you can replace your E with a W if you want. Okay, so let's look at some example problems of using the PET equation. So as I already said, you have the PET equation. So I have power, energy, time. So let's see, they're talking about lifting a baby from a crib takes 50 joules of work, and how much power is needed if the baby's lifted in 0.5 seconds. So we have 50 joules of work. Now we said the energy could also be work. So we have 50 joules, and so we have 0.5 seconds is time. So that means we're going to be solving for power, which is good because that's what the question is asking for. So P is equal to 50 over 0.5. So if we use our calculator, 50 divided by 0.5 is 100. So that's going to be 100 watts. Okay. Now if we look at the next one, again, you're going to be using the PET equation. P equals E over T. So P, E, T. So we look at this one, they're talking about a runner. They give you 130 watts. How much work is done by the runner in 10 minutes? So they give you 130 watts, so that's the power. They give you 10 minutes, but keep in mind that our time has to be in seconds. And so we just have to multiply that by 60 in order to get the number of seconds. So that's going to be 600. So, and we're going to solve for the amount of energy, or, again, work can be replaced. So 130 is equal to E over 600. So notice here, the setup, you're just going to have to multiply. If you have P, you have T, it's a multiplication problem. So 130 times 600, multiply those, So E is going to be equal to, in this case, 78,000. And energy or work is in joules. Alright, last but not least example. Again, we know it's a power problem, so you have your PET equation. P equals, E equals, and T equals. So the power produced by an electric motor is 500 watts. How long will it take the motor to do 10,000 joules of work? So they gave us 500 watts. They give us 10,000 joules. And so they want to know how long. So we're solving for T. So 500 equals 10,000 over T. So look at your setup here. So we're solving for T. If you want to, mathematically, this is just a flip. So actually it's going to be T is equal to 10,000 divided by 500. Or basically 100 divided by 5. So T is equal to 20 seconds. So there's an example of each one of those variables solving for the PET equation. So you could do some more practice in the 4.1 worksheet. Alright, I'm out.